So today I am going to be covering the solution to measuring the universe. To see if the universe is infinite or not. So today I don't have pages open. I'm just gonna make a new document. Wait. So today we'll be attempting to measure the universe. So we're trying to find out if it is finite or infinite. Now this video is exclusively made for my friend, my very best friend actually. Been friends with him for 8.5 years. So yeah, so I got a lot of history with him, and today I'll be making a video on why on the solution that I found that makes that could measure whether the universe is infinite or not. So see this equation over here. So my friend said that he does not understand what this entire thing means. Now, I assume he's lying because he's better at math than me. So, to cover what this means, first we have to envision if the finite universe, a sphere, universe, a universe with the shape of a sphere, is definitely gonna be finite. Why? Because because you see, this is our universe, and a sphere is not infinite because it can be measured out with cones. Like it could be measured out with finite points on it. So it means that so pretend this is our cone. Now this is not to like scale. The party hat can be extremely small, but the resulting number is still finite. I'll prove this to you in the next video, or maybe in this video. I don't know. So this is the solution to this hypothetical proven theorem that a sphere is always finite, yet other shapes are always infinite. So if you want to learn more about this kind of problem, like if you want a better proof than my proofs on why this is finite, check out the Poincaré papers written by I forgot what his name is. Like so the person who solved the Millennium question for the Poincaré conjecture. So this is related to that. So read the person's papers. They are very good. It's very interesting, inspiring. So over here, this equation states that m contains these dots. So these represent dots. So these dots represent So basically, these dots are this notation represents the dot on the top of the cone. So it means that this one dot represents this area, which can be epsilon. So this says it contains all of these dots, all the way until n-1. So this is the amount of dots. This is the amount of party hats that you put in it. So now since this is finite, I have not put infinity yet. I put n. So point n-1 all the way until point 1. So all of these points is much more larger than this set minus minus wait, let me see. Yes, so this entire collection, like this entire set of points, will always be larger than m, which means that this represents all the finite points, and this represents uh a collapse function. So it means, okay, I might go on to wrong terminology here, but this means it collapses. Okay, so this means that when it collapses, it means that I delete this, and only the points are remaining, and they create a new sphere. So this larger sphere that is created by the raised party hats will always be larger than the finite points given over here. So what I'm trying to represent is that imagine this thing is filled with these points. Now they're all encircling the sphere. Now this basically means that the set minus this amount of finite points will always, so the set is basically this set which contains all the possible combinations, which all contains all the possible points that could be inscribed onto the circle. This basically means all the points counted out. So this is countable, and this is uncountable. So it's uncountable. So it's countable that is larger than uncountable minus countable infinities. So, and then this equation basically states that if this is true, so you see this. So this contains this. So if you deduct this set from if you deducted this set from this superset, it will be less than this countable set, which proves that the universe is finite. So if the combination of this set is smaller than this of the superset containing this set, then the universe is finite. Which basically means if this equation is true, then the universe is finite. Now, most people say that this is stupid. I haven't covered this entirely. Like I haven't spoken this in any clear language. So yeah, apologies for that. I wrote this during my Chinese class, so yeah, I forgot most of it because I had Chinese 2 days ago, I think. So basically, the party hat solution is this. Now, to prove that a sphere is finite, we have to imagine now the Poincare conjecture. I have to pull out the Poincare conjecture. So I won't be doing this Wikipedia sourcing again. So I won't be doing that today. So the Poincare conjecture is basically means that it means that you could shrink a sphere infinitely. You could you could mold the sphere in any way, and it'll still be able to be wait, hold on. So imagine a sphere and a torus. So give me a sec. Imagine this sphere and a torus. So this torus can be a stretched bent, but it can't be it can be obstructed in some certain way. So wait, give me a sec. I need to search up. What's this again? Poincare conjecture. Okay, got it. So basically, it means that any object that has a surface. So let's pretend this is the surface. The edges can be connected to the other edges So for example, I could connect like all these edges to all the other edges. Now they'll be eventually molded into a sphere. Now this is the proof for this. Now the proof for this is already written. Now why this is finite. Now this is finite since the amount of particles can't be infinite, or else the particles would be zero, which renders them non-existent. So okay, so basically what this means is that if amount of particles is infinite. Give me a sec. Then they would be non-existent since 1 over infinity 1 over infinity is going to be equal to 0, or more accurately, this is going to be epsilon. So it's going to be epsilon, which means that they should be a non-existent, which means that they shouldn't count. So it must be finite. Yeah, other shapes can be infinite, because these other shapes let me think. So basically a sphere is finite because of this law. Now other shapes can be infinite because they are wait let me think. I'll come back in a second. Okay, so imagine that you want to comb this sphere. Now you'll be able to comb the sphere, but you cannot comb the sphere entirely. Now it's always going to be hairy at some point. Now these shapes can be combed since they have no continuous surface. What I mean is like they have a definitive edge that where you could stop the. So wait. So basically, this is a sphere, right? If we try to wrap it with some string, you could never fully wrap it without having space uncounted. So you could do this to a donut, since when it comes unwrapped, it looks like this, which is non-continuous. Now a sphere when unwrapped will have some edges extending to. Actually, I never unwrapped a sphere. I do not know what it looks like, but I do know that when it's unwrapped, it will have some edges that go on to continue to infinity, but forever getting smaller. So, which means that this might sound twisted, but I have to simplify this a lot. If you can't trace out the things that you can't trace out the entire sphere, it will go as unseen, which means that it will also be non-existent, which means that the sphere's size. So wait, let me pull out this equation. So the sphere's area, which we'll say A. So A for the sphere's area is gonna approach infinity but never get there, because it'll still have some space left uncounted for when you cover with the string, which means that the infinite space means that if you cover the finite space will never overrule the infinite space. It means uncountable infinity to be covered with countable infinity, which is not possible. Bigger infinities than others. So that's it. That's my proof, and that's my twisted video for today. I'll be coming up. A cinematic video will be coming up with a properly worded script. So yeah.